Okay, so let's actually head back to the last slide that we were on with solar masses between 0.25 and 4, and, pardon me, with stellar masses between 0.25 and 4 solar masses, and between 4 and 8. So the main thing is we have these elements that are pretty much the final products that you would have in these stars, as far as what they're capable of fusing up to. With carbon and oxygen, you have atomic numbers that are 6 and 8. With oxygen, neon, and magnesium, you have atomic numbers from 8, 10, and 12. So continually combining like helium, beryllium, together with these other elements, fusing up to these heavier elements. So what ends up happening is that with stars, let's move back to stars above 8 solar masses now. So in this case, between each period of fusion, the star is going to contract and expand and produce these other elements, like we had mentioned. And what you end up doing is going into a new red giant phase each time you have a contraction, then fusion, and having an expansion from the fusion. So this is the idea here. You have all these different cores that end up building up, and you end up going, as we set up to magnesium, all the way through silicon and up to iron. When you have iron like this building up, okay, in the core, fusion is going to end up ceasing because you can't fuse beyond. It's not energetically possible, at least within the core of a star, to fuse beyond iron. So once we get iron, fusion is going to cease, and the core is going to contract rapidly. You no longer have fusion, the radiative pressure pushing it out. So what ends up happening is that the fusion core, right, has a bunch of gamma photons left over in it. These are going to end up ripping apart and colliding with, the iron nuclei and ripping them apart. And it's going to end up breaking these particles, these nuclei apart into alpha particles and even smaller protons, electrons, and neutrons, okay, as the core condenses, okay? So the core brings together all this gamma radiation and these iron nuclei, and what happens is that the electrons end up being forced into protons as gravity takes over, just like, before we had just everything coming close together. Well, here they're actually being forced into each other, and you end up getting neutrons being produced, and lots of neutrinos come from these productions of neutrons, along with a lot of energy. And what ends up happening is that we have this continuous forcing of electrons into protons and forming neutrons, and the neutrons are going to end up pulling together and becoming very dense. And as they pull together, they're going to get so close that because of the Pauli exclusion principle, they're not going to be able to be allowed to share the same quantum states. But since they kind of overshoot, they're going to rebound, okay? And that rebound produces an outward pressure wave that's going to end up ripping apart the outer layers. And it's so energetic because the contraction is so rapid there, you end up with what we call, what this is a type 2 supernova. And it's a common supernova for stars this size. So this is, the common fate for stars that that are above 8 solar masses. Now, what exactly happens, though? Okay, whether you end up with a neutron star, black hole, white dwarf, depends on the amount of mass that you have. Okay, within the core. So, like we were saying before, you have those stars that have masses between 0 and 8 solar masses. Okay, so right here on this scale, we're looking at it's the difference between these stars right here. That's the line that kind of splits them. All right. What we end up with here, okay. Sorry, that should really be. We should really take us. Let's see. Over here. I guess maybe I haven't drawn perfectly enough there, but when we have between 0 and 8, you're going to have everything that's going to lead you up to a white dwarf. All right. So, like I said, that's going to go from the main sequence to a giant. Okay. And then depending on how much mass you have, if you're lower on that scale, you're just going to go straight to a white dwarf, or you're going to have that little puff, all right, of that red giant stage, and swelling down. Pardon me. You're not going to have the puff. You're going to swell up, down, and go back up. And that's what's called the helium flash. When you start to fuse helium, after you've contracted, you're going to turn blue for a little bit, and then come back up to these other colors. All right. Yeah, after a while you become planetary nebula, and what you have left over is that white dwarf that we talked about. So there's actually a limit, okay, that depending on how much of the core is left, okay, you're going to end up with this white dwarf. And that white dwarf is stable, okay, and this was shown by Subrahman Chandrasekhar, okay, this famous Indian physicist, that a white dwarf is stable at a core mass, okay, of less than 1.4 solar masses. So this is the white dwarf we're talking about, that mass being contained within the volume of something that's the size of the Earth. So if we end up with more than this, okay, if there's more, which is why I think, in this graph it's possible, to be between 0 and 8 solar masses and still end up with a neutron star, all right? If it's more, all right, the electrons forced into protons, forming neutrons, and we get our neutron star. And that's because the gravitational collapse is just going to be too strong there. So we end up with a neutron star. Now, there's another limit. Okay, we were talking about this before with stars typically over 8 solar masses, which is known as the Oppenheimer-Volkoff limit. Okay, so the neutron star is going to be stable. This is the core. Okay. Isn't more than 3 solar masses. Alright, so beyond this, if there's more, just like before when we had a situation where it produced a neutron star from a white dwarf, that limit, here if it's more, it will produce a black hole. And the reason for this is that the gravitational field ends up becoming so strong that it curves in on itself, and as we know, light itself cannot escape from a black hole. Okay? So, like I said, black hole gravitational collapse is so large, so much mass being shoved into such a small area, nothing there to stop it. Light itself cannot escape. So we cannot detect them. So we need indirect observation to see them, right? And some of the ways that we can look for them, sometimes they're in binary systems. And you look for X-rays given off as particles that accelerate into the black hole. That's typically the telltale signature is these particles accelerate in, they get really, really fast, and their acceleration is really strong, and that's going to produce, X-rays and some gamma ray sources, and that's what we think are, that's our evidence for black holes. Some of it at least. So, neutron stars. Okay, we talked about this already. This is thought to be the result of a supernova. Okay. And they are incredibly dense. We talk about white dwarf being dense, and obviously black holes being incredibly dense, or actually, I suppose it's, to the point where it's infinitely dense, the singularity within them. Neutron stars are in between them. Okay, so thought to be a result of a star above 8 solar masses having a supernova. All right, and so before with white dwarfs. We talk about electron degeneracy pressure, which is basically, electrons not being able to occupy the same quantum state, causing white dwarfs to be stable. With neutron stars, it's the same kind of concept, applying the Pauli exclusion principle here. All right. So the last piece that you need to know about here are pulsars, and these are rotating neutron stars on an axis. Okay, that is different from magnetic field rotation. So when we go to Green Bank, West Virginia, you guys will be able to actually, they'll have a little bit of an exhibit on this. So neutron stars, when they rotate so rapidly they end up actually producing radio waves. And those radio waves end up being produced here in a cone of light, actually, that ends up being spit out through their magnetic field. Okay? But if this whole thing is rotating about an axis, all right, that's through it like this, while the magnetic field is on a separate axis, all right, it's going to spin around like a lighthouse almost, flashing us every so often as it passes by. Okay? So yeah, that's just a little something there for a pulsar. Yeah, that's it for the evolution of stars, what you need to know. You should be familiar, just in terms of depending on the mass of the star, what the different sequences are. I would recommend, okay, just looking through this, just to go through it again here. The normal main sequence star is going to go through, its lifetime forming from a protostar and end up becoming a red giant and then becoming a helium-burning star and maybe going through a second red giant phase and then ending up puffing out its outer atmospheres and becoming a white dwarf, okay, after puffing off in a planetary nebula. But stars above, 8 solar masses, and you see here, I know it says 25 solar masses, okay? Start with the, protostar, go into a blue main sequence star, so, really high luminosity, becomes a red supergiant, becomes a helium-burning supergiant, and then goes on to a multiple shell burning supergiant, and it can, go between a few different supergiant phases here, and eventually will become a supernova that will, in its center, either produce a neutron star or a black hole. These are the two main paths that you should be familiar with. All right. And again, looking at something like this on the, looking at the HR diagram here. Okay. Where these stars end up. It's all about where they start with here, and this luminosity depends on what their mass is. And you can see here the different regions, the red giants, red supergiants, blue supergiants, what stars occupy them from this graph here as well. All right? So go between those graphs, and yeah, a few more notes on stellar distances, and then we'll talk about this more on Wednesday.